Algebras. Welcome to your Chapter 11 Lesson 2 notes, all about finding the axis of symmetry and vertex using algebra. Now, let's just review graphically how to identify the different pieces of a parabola, these characteristics that really make a parabola more unique. Okay? And these characteristics are the axis of symmetry, this vertical line that cuts our parabola in half, and where we draw that line, each side of the parabola could fold and be together, right? And be matched up. That's why we call it symmetry. The y-intercept is the point where the parabola touches the y-axis. It is a point, and it's where your x value is 0, okay? Next, we have the vertex, and the vertex is right here, this point on the axis of symmetry, where the parabola actually makes that turn. The vertex is sometimes known as the turning point as well, but it is an xy point. The x value matches the x of the equation of the axis of symmetry, and the y value, of course, is for this coordinate right here. And lastly, the zeros or roots or x-intercepts, however you want to say that, are where the parabola touches and crosses the x-axis. Okay? These values always have a y value. These points, always have a y value of 0 because they're right on the x-axis. And that's, of course, where the y value is 0. Okay? So what we're going to do is we're going to learn today how to find the values of these given the function equation only. I'm going to use my graphing calculator to check my results, but I'm going to have to learn how to do these algebraically as well. And they all stem back to actually having memorized the quadratic formula back in chapter 10. So in chapter 10, we learned all about that fantastic quadratic formula and then how to plug our standard form quadratic equations into the A, B, and C slots in the formula to get out our x-intercepts, okay? Now what we're going to do is we're going to use the pieces of the quadratic formula, the negative b over 2a. Remember, this is the full formula. And we know that this plus and minus square root of b squared minus 4ac, we know we referred to that as the discriminant because it determined the types of roots we were going to have. But look, there's your axis of symmetry formula right here. If we just plug in the b and the a values from standard form of our quadratic function equation, we can figure out what will be the equation of the line that cuts this parabola in half. Whereas this part right here helped us determine the types of roots. That part, the discriminant, helped us determine, did we have 0 real roots, meaning there was a negative number under there? Did we have 1 real root, meaning there was a 0 under there? Or did we have 2 real roots, meaning there was any positive value under that radical? Okay, so this formula is so awesome because not only does it help us solve a quadratic equation for x, it also helps us to then determine the types of roots or find the equation of the axis of symmetry when this equation is now put in function form. So it works on tons of levels, okay? Now what we're going to do is we're going to use this formula with this example, y equals x squared minus 6x plus 8 as our function equation example. We're going to plug our a and our b into this formula and simplify, and we're going to find out what the equation of our axis of symmetry is for this formula. Okay, so let me zoom out just slightly so that we have a little bit more room here to work. So write the formula of the axis of symmetry, x equals negative b over 2a. Okay, We have minus whatever our b value is. Well, our b value is the number in front of the x, so it's negative 6, over 2 times our a value is whatever the number is in front of x squared, positive 1. Negative of negative 6 is 6. 2 times 1 is 2. Can 6 evenly divide by 2? Yes, we get 3. That means the equation of our axis of symmetry of this function is x equals 3. Can I check it? Yes. So while I have to use this when I'm told to solve algebraically, I can use my graphing calculator to check my answer to make sure it's correct. So press y equals, clear out anything that's already in here, and then in y1, let's type in the function equation, x squared minus 6x plus 8, and graph it. Now let's see, we can clearly see that right about here is the vertical line that will cut this parabola in half, right? But let's just double check what that is. So second end graph gets us the actual individual points, okay? So what I'm gonna do is look at my y's and say, okay, I need the axis of symmetry and turning point kind of in the middle. This goes back to chapter 3 when we were graphing these, right? So let's kind of arrow up so we can start to see that pattern in the y's repeat itself. Okay, so we're looking at, okay, we can start to graph 0, 8, and then we've got here, here, here. Okay, look, we get down to negative 1, and then it turns back around y value-wise. That tells me that this is the turning point, 3, negative 1, which tells me that the axis of symmetry equation is x equals 3. Exactly what we did algebraically right here. Okay, so speaking of, I can also use that to find the vertex. Now, there's two things we can use with our function equation to help us with the vertex, okay? Those two things are, we can actually find the value of y for the vertex by taking the x we just found as our x value for our axis of symmetry and plugging that back into the equation and solving for y. That'll give us the y value that matches that x value of the point, okay? Yes, right now, since I just checked for my axis of symmetry, I'm actually going to know what that vertex is going in, which will be helpful. Next, the other thing the equation of my function can tell me is if my parabola is frowny face or smiley face, right? I referenced that in lesson 1. A parabola that opens upward like this, I reference as smiley face, and there's a specific reason for that. If your a value, the number in front of your x squared, is positive, you're going to see a smiley face parabola or a parabola that opens upward. And positive people tend to be who you think of as smiley. Well, that means that if these are smiley face parabolas that have a values that are greater than 1, or 1 or greater, I should say, then you have a bottom to it. That predicts that your vertex is going to be the minimum. Smiley face parabolas, the vertex is a minimum. On the other side of that, if your a value is negative 1 or lower, so a negative number in front of your x squared, you're going to get a frowny face parabola. It opens downward. I refer to this as frowny face because we think of negative people having frowny faces. And if your a value is negative, you'll have this parabola that also has a top, a maximum. So if you can have that association in your head, then it makes it so much easier to predict, looking at your function equation right off the bat, is your vertex the highest point or the lowest point? Okay, so the two things we'll do this time using our y equals x squared minus 6x plus 8 is we're going to find the matching y value. So we're going to state the coordinate that is the vertex of this function. And we're going to state whether that vertex is the highest point or the lowest point, a maximum or a minimum. So we had from the front the axis of symmetry of this function being x equals 3. So what we're going to do now is we're going to replace x with 3 in the equation to find the matching y value. And so really algebraically, that's the only step you need to show me. Okay, I can do this in my head, but I do have this calculator that can help me do the calculation if I plug this in. So 3 squared, and again, in parentheses squared, minus 6 times 3 plus 8 will give me negative 1. So that means the matching y value for this x value of 3 is negative 1. That means the turning point coordinates are 3 comma negative 1. Now again, this x squared is positive, so this is a smiley face parabola. So this has a bottom, this turning point is a minimum. We know that already because we already saw this parabola graphed in its smiley face, and we already saw its turning point was 3 negative 1. So that's our check back to make sure we've done this algebra correctly. If you want to find the y-intercept, then you want to replace x with 0 in the function. So algebraically finding the y-intercept means plugging in an x value of 0 in this equation, okay? Because we know that with the y-intercept, x is always a value of 0 for that. So y equals 0 squared minus 6 times 0 plus 8. Well, this works out really well because anything times 0 is 0 and 0 squared is 0. So what's the only thing left here? 8. See that? It's the only thing left. So actually, you can predict the the y-intercept value by just looking at the constant at the end. The y-intercept is going to be 0, 8. Oops. Because the constant at the end was 8. And these guys are going to zero out because I plug x values of 0 in. See that? That's kind of neat, isn't it? All right, last ones. Oh, last thing I wanted to mention, right? I know that the overview of chapter 11 kind of mentions that we'll find the roots algebraically. That's actually what we've been doing throughout chapter 8 and 10. When we are solving quadratic equations for x, we're finding the x-intercepts, the zeros, the roots of our parabola, right? We're replacing y with 0 and we're solving those. That's why those equations are x-only equations. That's why that's the only variable involved. So it's really neat that that comes back and forth. All that thing that we've been doing in chapter 8 and chapter 10 of solving quadratic equations now comes to light as the algebraic side. And we're going to do that on question 3, okay, together. But what I want to start with is on question 1. I want to do this part together. Okay, we're going to find the axis of symmetry, the vertex, whether it's a maximum or a minimum, and the y-intercept algebraically. All right, I'm going to plug right in here and do that. And what I first notice is that I need my function in y equals ax squared plus bx plus c form, and I have that. So even though there's not a c at the end, it's still in standard form of a quadratic function. So I want to use for my axis of symmetry equation, x equals negative b over 2a, the front and bottom parts of the quadratic formula. I'm going to plug in the negative of negative 18 divided by 2 times 3. So we've got positive 18 divided by 6, which of course ends up being 3. So my axis of symmetry equation is x equals 3. We always, always, always write our axis of symmetry as an equation of x equals whatever that value is, because this is the equation of the vertical line that cuts our parabola in half. So because this is a line, it requires an equation, x equals 3. Then we take that value and we plug it back into the original function everywhere we see x. This step, we can actually use our graphing calculator to help us plug in, just like we did here. So 3 times 3 squared minus 18, oops, my minus didn't take, sorry, minus 18 times 3, and see what we get. Okay, so we got negative 27. Yeah, that makes sense to me. And that means my turning point is 3, negative 27. And I look at my value in front of x squared. It's positive. So that means this is a smiley face parabola, which means there is a bottom. So that turning point is a minimum. Now, lastly, for the y-intercept, I plug in an x value of 0 here in both spots. And remember, I told you to look at the c term at the end to predict the y-intercept. Is there a c term at the end? It's 0, right? So the y-intercept is 0, 0. It's the origin. Because my value at the end is 0, when I go and plug the x values in of 0, I get 0 minus 0. Y equals 0. That's my y-intercept. Okay. This is where I would normally stop and have you try one, but I want to show you what's going to happen if our b term is negative. Okay, so I'll use a different color as I would when I normally would stop you, but I actually want to do this one together as well. The b term is negative. We haven't seen that yet. We tend to deal in even b terms because they evenly divide by our 2 at the bottom. However, we don't have that every single time. So here is a place where my b term is not even. So when I go to plug that in, I have the negative of negative 5 divided by 2 times 1, and I get 5 over 2. Can that evenly divide? No. If you want to plug it into your graphing calculator to get its decimal equivalent, you may, but we don't have to. We can leave it as 5 over 2, okay? So our axis of symmetry equation is x equals 5 halves, or we can say x equals 2.5. Now, what that does mean is, yes, I have to plug that fraction in multiplied in the original equation to get my matching y for this axis of symmetry and turning point combo. So let me write it out first. I went to go plug it into my graphing calculator, but let me write it out first. 5 halves squared minus 5 times 5 halves plus 8, likely going to give me a fractional or decimal y value as well. Let's take a peek. 5 halves squared minus 5 times 5 halves plus 8. And what do I get? 1.75. Let's change that into fraction form. So math, and then enter, enter, changes that into 7/4. So I'll have both. Okay? So my turning point is 5 halves, comma 7/4, or 2.5, comma 1.75, depending on your comfort level. I do need to know if my turning point is a maximum or a minimum. And so in this case, my x squared is positive. That means a smiley face. That means a bottom. That means my turning point is a minimum. Lastly, what's the value at the end of this? The constant at the end, that would be 8. So my y-intercept point is 0, 8. There you go. So what I'm showing you there is it's possible to have, the y-intercept point still be integers, and the turning point and axis of symmetry, it's very possible for those to be decimals and fractions. Okay, and you might run into that. And you'll know right away if your b value is an odd number that that's what you're dealing with. It just means that the line that cuts it in half is not on an integer plane. That's it. Okay, so what I'd like you to do for number 3, this is where I'll pause and have you do it yourself. What I'd like you to do for number 3 is I would like you to find the axis of symmetry equation using x equals negative b over 2a yourself. Find the vertex point, plugging in the x value from the axis of symmetry and finding the matching y. Tell me whether the vertex is a maximum or a minimum, the same way I did, just write it underneath, right? Tell me the x-intercept value, and then use completing the square or quadratic formula, or you can actually factor this one, to find the x-intercepts or the roots or the zeros, whatever word you want to use to describe that. But pull back from chapter 8 or chapter 10 to do that last piece. So the other 4 pieces I just taught you, this piece is a pullback from chapter 8 or chapter 10. So I want you to pause it right here and do that right now, and then we'll close up together in a moment. Okay, here are my answers, and I'm going to now check all of that by plugging into my graphing calculator. Okay, so let me clear this guy out. Let me go to y equals. Let me go in here and plug in x squared plus 4x minus 5. Press graph to see it. Okay. Press second in graph to see the table, and I need to have that pattern going on in the y's. So I'm arrowing up. Oh, I arrowed up a little bit too far. There we go, arrowed up. Look at that. Axis of symmetry is x equals -2. Turning point is -2, -9. Y-intercept is -5, 0. And then we've got the roots also have, oh, sorry, I said that wrong. Excuse me. 0, -5 is the y-intercept, my bad. 0 needs to be the x for the y-intercept, duh. And then these -5, 0, and 1, 0 are the roots where the parabola is touching or crossing the x-axis. And let's just go back real quick that this turning point is a minimum. Now look, where we're touching or crossing the x-axis, x value of -5, x value of +1. All of that pictured right here. So all of the things that I was talking about right here, okay, all these match back up to this graph. So algebraically and graphically, we need to be able to go back and forth. If you're asked to find the axis of symmetry algebraically, sure, you can go to your graphing calculator and plug in the function and find the axis of symmetry looking at the table or looking at the graph, right? But if I ask you to do it algebraically, you must plug into x equals -b over 2a. If I ask you to find the turning point algebraically, you must plug into the function equation with the axis of symmetry x value. If I ask you to find the y-intercept algebraically, you've got to look at the equation and say, oh, this is the number at the end. There's the c value, right? So you have to do all of those pieces. Okay? Well, if you need help with any of these pieces, please do not hesitate to ask. Remember, you've got to know what these pieces on the parabola are. Oops, a little too much there. Okay, so please make sure you can identify those looking at the graph and that you can also match back up algebraically. Good luck. Let me know what you need and when you need it. This has been your Chapter 11 Lesson 2 notes. I look forward to doing this with you. Have fun, guys. Bye.